morning, everyone. Thank you for tuning in to my channel. So, where to begin? Well, I'm programming my PIC10F200 and I'm trying to get it to control a shift register, the 74HC595. I didn't look elsewhere for source code. Well, actually I did, but I couldn't find anything. So I thought I should have a go at creating some code to control the shift register. Alright, so leading up to the creation of this video, I've been working on understanding and using the shift register and doing that with manual control, using my fingers to control the inputs on the shift register. To do that, I actually created a separate module out of popsicle sticks which debounced all of the switches and created 8 digital outputs controlled by 4 debounced switches. If that's really interesting, hopefully I leave a link in the description below for these videos, but you can also search for these on my channel. So things are a work in progress. The next step for me is to get my PIC10F200 chip to control the shift register the same way I was doing manually with my fingers. So, a word of warning that that's a lot of information, requisite knowledge for the sake of understanding this video. So this very well may be confusing to watch or hard to understand. It's hard for me. Maybe I'm not that smart. So this is a work in progress, and it's not really at a stage where I want it to be, but I did achieve success in controlling the shift register, and what I was able to do is send out a value on the PIC10F200, which I'm programming here, and just send that value serially, bit by bit, to the shift register. And I did that successfully because I got the number here to show up on the shift register in the form of highs and lows using LEDs attached to the shift register. So just to prove that I can do this, I'll pick the number 11101010. And when I get to the video clip of my breadboard 10F200 setup, it should be evident that I get this number to appear on the shift register. It's an achievement for me, not to brag, I'm certainly not, but it's not doing what I want it to do completely, because what I'd like to do is have the PIC10F200 operate as a counter, counting from 0 to 255. So I created an equate to store a counter value, but I haven't implemented that in my code yet. The basic thing I wanted was just to take a number and get it to spit it out on the shift register. The other thing I need to do is have another delay, which is much shorter. I'm using like a 1 second delay here that's too long, and the delay appears everywhere. So I need to create a couple different delay times to speed up the process. So hopefully, not in this video, but in my next video, I'll have been able to achieve a PIC10F200 chip that is a counter, and as it counts up, it'll transmit those bits serially into the shift register, which will count up and display that information through parallel ports and show a whole byte of information as it progressively counts from 0 to 255. That is my goal. Anyway, enough yakking. Hopefully that explains things. So I did set the mClear on. These are equates used for the counter, for the delay down here. If you've watched previous videos, I've been using that same delay. I'd like to get away from this method and actually use the timer as a delay, as I've done in PIC18 projects, but that's getting off topic. So I'm still using this primitive caveman method of creating equates and inner and outer loops in a delay routine. Can it be done better? I'm not even sure yet. So anyway, this is org. This is where the code starts, and the way I've initialized things, having watched previous videos, I didn't realize that GPIO pin 2 is a bit of a trick to set up as an output pin, and this deserves a separate explanation. My last PIC10F200 video discusses this. I get all grumpy in the video, but I realize that's actually necessary now. So you can do it this way, as somebody has done, which is really confusing to try to understand what it's doing, but I hopefully correctly figured that this is actually the binary value that this represents, and to understand this fully, you have to look at the data sheet in the option register of the PIC10F200. Okay, if anybody who has worked with the 10F200 chip might already know, it has 4 output GPIO pins, but here's GP0, 1, 2, and 3. GP3 pin is an input only. That's why there's a 1 here. You can't configure that as an output pin, although you can configure GP3 as an mClear pin. These rest of these number 1s are meaningless because they don't match up with any of the GPIO pins. You could put any numbers here. You could put 0, 0. It doesn't matter. It's just these 4 least significant bits that set the GPIO pins. So, without really explaining it over again from my past videos, to control the shift register, I need at least 3 output pins from the 10F200. This GP3 could be implemented in different ways. Maybe I could get a 555 timer controlling the rate. Maybe I could get a 555 timer on GP3 as an input pin, taking in a timer signal, and maybe that could be the speed and rate at which the whole project counts. I'm going to make this 10F200 project a counter as displayed on a shift register. So maybe if I use GP3 correctly, I can get that adjustable as the rate of counting using a 555 timer? Maybe. Okay, so this sets up 3 of the 4 pins as outputs, and then GP3 is an input. It has to be. And then, just to initialize it, I'm sending the 2 GPIO pins, GP0 and GP1, lows. But there's a reason I'm sending GP2 as a high, and that's because it controls the L clock pin on the shift register, which is normally high, and it spits out the data in memory on the parallel lines when it's brought to low. So GP2 had to be set high, and I designated GP2 pin as the pin that's going to control that L clock. I even left a comment about that. Set all output GPIO to low except L clock. It doesn't really matter what we set GP3 as because it's not an output pin and all of these bits don't matter. But it's done on this next line. It takes this number, it's moved into the working register, and then here it's moved from the working register into the GPIO file and the file register. Here's the main loop. Once again, I think I'd like to have some counting action going on, incrementing a stored counter value in the C1. So that's a work in progress. This is from a previous Blink sketch, that's why I commented it out. Here is where I'm going to maybe increment this file stored value. Okay, so then it goes into testing each bit of counter value 1, which I just gave it a fixed value. And then it counts, it's going to test each bit. So bit test file skip if clear. And what file is it testing? It's going to test this C1, which is my equate for the storage counter. And I just assigned that storage counter this value for the time being, just to simplify the code and develop it in stages. So I'm bit testing this C1, which has this value, and this says to test this 0 bit. And we're testing if it's clear, and we're going to skip if it's clear. So it is clear, it's a 0. So then we'll skip over this line. Now if it was set, then this next line would also set GPIO pin, GP0. And GP0 is the bit that is going to control, okay, I'll write it down, GP0 controls the serial input on the shift register. And then whatever GP0 value is there, it gets clocked. And when you use the shift register, there's a routine kind of sequence of button presses. So I decided to make that a separate subroutine. So after a brief delay, it calls this shift register code, which is a subroutine, which is down here. Hopefully I can explain this. So these are kind of like the routine button presses you may have seen me do in this video. So I'm sort of clocking in the serial input data. So I made that clocking of the data separate subroutine. And I just wrote a comment. This is the shift register subroutine. And what this will do is once it gets into this routine, I'm setting GP1 high, and this is connected to the clock pin, which is activated with a high. So it'll take what's on the serial input, and then because it's sending GP1 high, GP1 clocks it in there. And then a delay, and then I send GP1 low again, and then a delay, and now I set GP0 low. GP0 is the serial. GP0 is the serial in line for the info for the data that it's sending to the shift register. But I also have to send that low as well. Then a delay. And MPLAB doesn't seem to like me using the return opcode or command. So I've been using this retlw and just putting a 0 after it. It's sort of like returning a 0 value at the end. But then when this shift code subroutine is run through and the first bit of data is clocked into the shift register, it returns back like maybe here. After here it goes to here, and now it's checking the next bit of data, which happens to be a 1. Bit test file skip if clear, and we're bit testing bit 1. Well, bit 1 is a 1. It's not clear, so it won't skip if it's clear. So it'll set GP0 high. Once again, GP0 is the data going into the serial input line. But then again, it calls a delay, and then it goes back to the shift code, which is again the shift register subroutine, and it'll bit set F GP1 high to clock in that data, and then it'll go low again, and we'll clear GP0, which is the serial input pin, and we'll return back up to add the next bit of data, which is bit 2, 0, 1, 2, which is a 0. And it goes through each of the 8 bits. Of course, it starts at counting at 0, so it's 0 to 7 bits, but that's 8 bits. And yeah, it clocks in this number. So just a few reminders. If somebody was by chance trying to replicate what I'm doing, that's giving myself a compliment. I don't know if people actually are even doing that. Not many people watch my videos, but a few do, so thank you for watching. But just a few words of reminder. The 74HC595 has to have a little bit of setup. The output enable pin has to be set to low. The reset pin has to be set to high, which actually can be used in code form. I might actually add that in, but the PIC10F200 only has a limited number of output pins. So some things to work on, like, is there a way to not have to retype out each bit like this, 0, 1, 2, 3, 4, 5, 6, and 7? Could I somehow reduce the number of lines of code by implementing a counter? I'm thinking it is possible. It's hard for me to think that through. And as I said already, rather than just sending a fixed value, I think it'd be really neat to have this equate counter incrementing with like an incf, and I can increment through the numbers and then display that on the shift register. That may not be that impressive. I actually did that in a previous video. Like, I think I was showing off my binary to decimal conversion, which kit, which is an Arduino really, and it's just an Arduino project. But I also created a counter. Oh yeah, okay. I guess back at video 10 in my 18F4525 video series, I created a counter counting from 0 to 255. So it's not hard to do with an 18F chip. There's more opcodes. You can use the move FF instruction, and you can create all kinds of counters, and it's a little easier to do. But here I'm not just creating a counter, I'm controlling a shift register. And the data output onto the shift register will be a counter. Okay, thanks for watching. The next video will be on my breadboard setup with my PIC10F200 board. And yeah, you'll see. Thanks for watching.
Alright, so I missed capturing the upload. Here's the reset pin, this orange one. It's tied to power. If I set it to ground, it should reset it. But that's not set up as an interrupt. The code is polling through, and there's a lot of delays in there. So there it went. It cleared everything. But if I set the reset pin back to 5 volts, and I will, you can't see it, but it should start the code again. And my real point is just to show that that number I put in counter C1, it should pop out here. It's like 1110101. I know that's thrilling, right? I shouldn't be so sarcastic, but yeah, look at that. So I got the shift register to do what I told it to. So there's my number. Thank you very much for watching. I do appreciate it. Have a good day. Take care.